Good morning, everyone. My name is Kirsten Emory, and my thesis title is the identification of short and long-lived radioisotope contamination in the stages of F18 FDG production using gamma spectrometry. My supervisors were Dr. Pejman Roshan Farazad, Janet Atkinson, Stephen Crosley, Dr. Joseph Iapolo, Ian Bucklow, and Roger Price. So to start with, F18 FDG is a radiopharmaceutical. Radiopharmaceuticals in general can be used for diagnostic and therapeutic purposes. Diagnostic tracers are used to investigate the presence of a suspected disorder, whereas therapeutic tracers are used are usually cytotoxic and are used to target specific pathological cells. In both of these cases, the radioisotope is chemically bound to the bioactive molecule and is suited to the biological process to be targeted in vivo. Radioisotopes are radioactive isotopes of an element. This means that they are unstable, and due to this excess energy in the nucleus, they undergo spontaneous decay. And this can be done in the following forms. We have alpha, beta, gamma, and positron emission and electron capture. These decay modes are key factors in deciding which isotope will be, whether it be used for diagnostic or therapeutic purposes. The desirable characteristics for a diagnostic isotope is that they must emit gamma rays or X-rays, and these emissions must have sufficient energy in order to escape the body and reach the detector elements. The radioisotope must also have a short half-life so that it decays soon after imaging the patient. The radioisotopic component of the radiopharmaceutical is used in nuclear medicine and, as I said before, decays via X-ray or gamma emission. For example, we have 2-deoxy-2-F18 fluoro-D-glucose, also known as F18 FDG. This is a positron-emitting radiolabeled glucose and is used in radio-oncology, neurology, and cardiology. Radioisotopes are also used to obtain diagnostic information in the form of 3D or projection images. The key modality used to perform these images is single photon emission computer tomography, SPECT, or positron emission tomography, PET. These images can also be fused with a CT or MRI, as the radiopharmaceutical will give you the functional information, and by fusing with CT or MRI, they'll give you the atomical information. So the SPECT CT provides three-dimensional images, which are generated by combining multiple projection images that have been taken at different angles around the patient. The PET CT also creates these three-dimensional images. However, the radiotracers used in PET actually produce positrons, which are then converted into gamma rays. The PET scanner then uses coincidence detection, line of response, or LOR, between the two of its detector elements, and many LORs are then combined to form an image of the radioisotope distribution in the patient. So this is also when annihilation occurs. The positrons collide with an electron, and they are converted into two 511 keV photons. These are released in opposite directions and cause a coincidence event. The PET scanner has a ring of detector elements, and when these photons hit the detector elements at the same time, a coincident event occurs, and this is how the LORs are created. So FDG is one of the most common PET radiotracers. It contains F18 nucleotide and is a positron emitter. It is extremely useful for identifying cells that are hypermetabolizing glucose, and thus it is very beneficial in areas such as oncology for diagnosis, disease staging, treatment, planning, and monitoring. F18 FDG F18 fluoride is produced in a cyclotron by a bombardment of F18 enriched water. The target is hit with a high energy proton beam, usually of up to 18 megaelectron volts. So the primary photon beam, along with the secondary field of neutrons, can produce unwanted activation products which contaminate the water target via spallation. The majority of these activation products are generated from proton bombardment of the component metals in the front foil of the target. There are strict international regulations that govern the pharmaceutical productions, and these require extensively pure products free of all radioactive contaminants to be formed. Many tests, such as gamma-ray spectrometry, can be used in order to QC. So the main foil at the front of the target is actually made of Havar. Havar itself is a cobalt-based alloy that is comprised of cobalt, chromium, iron, nickel, tungsten, molybdenum, magnesium, and carbon. It has a high thermal resistance and strength, and this is used as the main foil covering. So this is the process of F18 FDG production. So we start with the irradiation of the O18 enriched water with a proton beam of up to 18 megaelectron volts. And we have our Havar sitting here, which is the front foil. We then have our F18 ions. They pass through into the QMA column. The F18 ions are retained in this column, and then the enriched water is eluted through. The water then will come into the recovery vial, and that should also contain all the metal contaminants as well. So now we have the fluoride ions are still in the QMA column. They're then eluted off into a reaction chamber. After that, they are passed through a C18 column. This is where the protective groups are removed. Further purification is then done through an alumina column. This will remove any unreacted fluoride. The last filtration process is through a sterile filter. This removes any microbials that may have entered during the system. And then last but not least, we have our filtered F18 FDG product. So as I said before, I'll be using gamma spectrometry. So the identification of F18 and any radioactive contaminants in the FDG will be conducted using a high purity germanium gamma spectrometer. The information obtained from the gamma spectrometer is in the form of energy distributions, and the energy peaks from distributions can then be matched to any respective isotopes so they can be identified. The gamma detector is actually high purity germanium, so it's extremely sensitive and has a very high resolution. So the aims of this study is for the radioisotopic impurities to be identified over the different stages of F18 FDG production and purification using a gamma spectrometer. I analysed the following. So I had an old Havar window, and at the time of measurement it was 3 years old. I also analysed 2 new Havar windows, and they were removed from the Cyclotron in July 2019, so they were 2 months and 1 month old at the time of measurement. I also measured the unpurified fluoride in aqueous solution after it had been expelled from the target. We also have the recovered O18 water following the first purification step, the 3 solid phase extraction and purification cartridges, which were the QMA, alumina, and C18, and then last but not least, the purified F18 FDG. In terms of the published literature components that I can compare against, I could not find a paper that followed the full F18 FDG process. So what I've done is I have found 5 papers that at least looked at 2 elements of this process, and I've collaborated them together and then compared against each element that I've been looking at. As you can see, they mainly picked up cobalt contaminants, which is expected because Havar is mainly a cobalt alloy. I will also point out that 2 papers found cadmium-109. Now, the only reason why they found this is because they use a silver window here, whereas we use titanium, so I'm not expecting to find this one in any of my results. So before I begin to explain how I identified the peaks, I first had to make a database in order to kind of help myself along, because Havar actually had quite a lot of contaminants. It was just a jungle within the spectra trying to identify them all. So what I did was I created a database which would help myself along. I'm going to try and explain how I did that. So to start with, I knew that Havar is composed of a certain amount of elements, which are A, B, C, and D. I then know that these elements have stable isotopes. And it is these stable isotopes that are going to be irradiated with a proton beam of up to 18 megaelectron volts. When this stable isotope has been bombarded, it will have the following reactions, and these reactions are going to create unstable isotopes. It is these unstable isotopes that are going to be giving off these gamma peaks, and through this I can then trace back to which element has come back from the Havar. So for example, these are the elements within the Havar. If we break it down and we choose chromium, for example, we can see that chromium has 4 stable isotopes. If we now choose one of these stable isotopes, say chromium 50, we know that it has these reactions from using QTOL, which is an online database. If I now choose one of these unstable isotopes, it has these peaks. I did this for every single reaction, every single unstable isotope, and every single stable isotope, and then for every single element of Havar, which took me a very long time. Not only that, I also calibrated the gamma spectrometer. This is so I could have an accurate KEV when I was identifying my peaks in order to match them with my database. So now when I come to my materials, I analysed an old Havar window. So to start with, I just put the Havar window on my gamma spectrometer, and lo and behold, it became flooded. The Havar window was extremely radioactive. So next, I put the Havar on a GAF chromic film just to identify that the proton beam did hit the Havar in the middle. After that, 6 discs were removed from the Havar in order to separately analyse them on the gamma spectrometer so I can analyse them without flooding the detector. Next, I also analysed some new Havar windows. They were 1 and 2 months old. So as you can imagine, they were also extremely radioactive. So for these, only 2 holes were punched out. Due to handling time, 6 was going to give someone too much dose. When I placed these on the gamma spectrometer, again, they were flooded. So in order to analyse these samples, they were rubbed with sandpaper, and the sandpaper was then analysed on the gamma spectrometer. I also analysed an unpurified F18 fluoride sample. In order to make this sample, the usual cyclotron parameters were mimicked for making the F18 FDG. However, it was only on for a few seconds, so the product wouldn't be too radioactive. However, we still diluted it 100 times. Same for the recovered water. After being passed through the QMA column, I took the recovered water and placed that on the gamma spectrometer. With the SPE purification cartridges, there were 2 sets. I also placed them on there. And last but not least, I looked at the purified F18 FDG product. The purified F18 FDG was made in the morning and then analysed it that afternoon. So these are my results. This is what I got after placing them on the gamma spectrometer, and these are their spectras. So we have the old Havar window and the new Havar windows. The most predominant contaminants on our Havar foil were cobalt contaminants. The main thing I wanted to point out was that on the old Havar foil, I found cobalt-57, which has an extremely long half-life. And in order for that to pass 10 half-lives to decay, it would be about 8.5 years. So my recommendation to MTP is to keep these foils for about 8.5 years before they're disposed. Next, I analysed the unpurified F18 fluoride, and what I found was these contaminants were passed into the F18 fluoride. Next, I analysed the recovered water. I only found 9 contaminants in here, whereas I found 15 on the QMA cartridge. So this suggests that the majority of the contaminants were actually particles that got lodged into the QMA column, whereas not a lot of them were actually in the solution that was passed into the recovered water. As we go along, it passes through the C18 cartridge, and we can see that I only have 12 contaminants left. So the contaminants are slowly being incrementally removed. By the time we get to the alumina, there are only 5. So anything at this point is possible to get into the final product. However, you'll be relieved to know that there wasn't anything that I could find. You can see in this spectra that we do have some peaks at the lower end. This is because we have the content edge and content backscatter. This is natural, we should be seeing this. We also have some peaks in the lower end at 72, 75 and 85. These are not to worry because they're just characteristic peaks from the lead shielding. We also have some peaks in the higher end. This is from the iodine 131 pipes that run near the gamma spectrometer, and they were removed during the background subtraction. So again, we just have a nice 511 peaks. This was also confirmed to be F18 by doing a half-life check on it as well, which I got 109.15 minutes. We want 109.7, so I would say that's pretty close. So, after collaborating all of these into a table, these are my final results, but I'd first like to explain what the percentages represent. And in order to do that, I have to tell you how I identified the isotopes. So to start with, obviously I'm using my database. So when I use my database, I've collected the fingerprint of each isotope. So I know that cobalt-55 gives off all of these peaks. And what I did was I had all my samples and they gave me a list of channels and their energies. And for every single energy, I typed it into my MATLAB database. It would then give me a few isotopes that could possibly belong to that peak. And then through process of deduction, I would find the isotope that it belonged to. So, for example, beryllium-7 actually shares the 477 peak. However, I didn't find any other fingerprints of beryllium-7. Therefore, I found the other ones also belonging to cobalt-55, so I've been confident that this is actually in my sample. So as you can see here, this is the theoretical, what cobalt gives off, and this is what I found in my spectra. So if we match the peaks, I am pretty confident that I had this in my sample. So next, in order to identify what I call peak significance, which is just a term that's given for gamma spectrometry, I use the most predominant peak that the radioisotope gives off. So this one has a probability of 75%. So I then use the 931 peak across my samples. So as you can see in the table, I do have values that are over 100%. This is because peak significance is given as the following. So if you were to have a background of, say, 100 counts, in order for a peak to be significant, it must be over the threshold of 104 counts to be considered a peak. We can then get a peak that's at 200 counts and can therefore be 200%. This is why we have a peak significance of over 100, because it's not normalized. So now if I compare my results to other literature, we can see that I found very similar results. However, I was actually able to identify some isotopes that other literature was only able to predict. So as we see here, some literature predicted Ni57 and zinc-65. They did not find it, however I did. Same goes for Mn52. For the unpurified fluoride, I did not find some elements that the other literature did. However, I just think this is because my sample was extremely radioactive and these energies were in the lower end where it was quite noisy. Although I was able to pick these up later on in the cartridges, so I would say that it's possible that these isotopes were actually in this sample, just weren't able to be seen due to noise. Next, we can see in the recovered water. Again, as I explained before, the majority of the isotopes do get stuck on the QMA column, and just a few are eluted through into the recovered water. And then next, these are the isotopes that I found on the columns, and as you can see, they're slowly incrementally removed as we get to the alumina. and then thankfully have not found anything in the purified F18 FDG. So in conclusion, production of radiopharmaceuticals is tightly regulated at every stage to guarantee the high purity of the final product. Heavy metal contaminating radioisotopes occur in the cyclotron, and they are products of F18 FDG, and these must be removed. The results are from an extremely sensitive technique of high purity uranium gamma spectrometry, plus my custom software that I created in order to identify the contaminants at each stage over the procedure. They are all originated from the bombardment of the Havar foil and are progressively removed. The results in general accord with the published literature. However, I also found a few isotopes that other literature was not able to identify. I also found niobium-90, which no one else has actually identified as of yet. The niobium-90 comes from the molybdenum reaction chain. So for future work, I would suggest testing for specific activity. This is F19. So during the filtration of the F18 FDG, F19 is very chemically similar, so it's actually not removed during any of these stages. So it would be interesting to see what the purity of the F18 FDG is. I would also recommend testing the F18 FDG a lot longer after I did, just to be able to identify any longer-lived radioisotopes. I'd also suggest testing for non-radioactive trace contaminants, as I could only identify anything that was radioactive. Other measurements could have also been made on the unpurified F18 fluoride, recovered O18 water, and the SPE cartridges, just to also identify any longer-lived radioisotopes, as I measured these not long after. I could also include calculations for the secondary neutron flux into my database. However, I didn't see this as a good contribution at the time, as these effects are quite negligible. These are my acknowledgements, so I'd like to say thank you to all of my supervisors for their assistance in my project needs, to all my fellow classmates, especially Kelly and Sinead. They've been really good with all their emotional support. I'd also like to thank my colleagues at Medical Technology and Physics for their understanding of my time pressures and assistance. And I would also like to thank the Medical Technology and Physics Department at Sir Charles Gairdner Hospital for allowing me to use their equipment such as the gamma spectrometer and the cyclotron for the use of my project. That is my conclusion. Does anyone have any questions?